Hello, and welcome to our NASA panel, See the Cosmos, NASA's James Webb Space Telescope. This year, we're launching this amazing telescope out into space, and it was recently called NASA's Golden Surfer by the New York Times. So it's a very exciting upcoming mission. So here today, we have a panel of NASA experts for you to speak to. So could you please introduce yourselves, everyone, starting with Amber?
Hi, I'm Amber Strawn. I am an astrophysicist at NASA's Goddard Space Flight Center, where actually all of us are from, I believe. I'm on the James Webb Space Telescope Project Science team, which is the team that works alongside the engineers during the development of the telescope. My specific area of research is extragalactic astrophysics. I study how stars and black holes form in distant galaxies.
Thanks, Amber. How about Stephanie?
Hi, I'm Stephanie Milam. I'm a planetary scientist at Goddard and also part of the project team. I have a unique role with the project in that it was my job to make sure that this amazing astrophysics observatory could actually do observations in our own solar system. And so that is what I'm here to represent today.
Wonderful, thanks. And Kenny?
Hey everyone, how you doing? My name is Kenny Harris. I am an engineer at NASA Goddard Space Flight Center. I was one of the guys in that full bunny suit, where you can only see kind of like this part of their eyes. So I helped integrate the satellite, which basically means put it together. There was some design and some testing in there as well that we'll kind of get into more throughout this conversation. But clean room integration, test and harnessing electronic components, and really being hands-on with the satellite. So I'm happy to be here today.
Thanks, Kenny. Nicole?
Cologne, and I'm also an astrophysicist at Goddard Space Flight Center on the project science team, along with Amber and Stephanie. And what I do is search for and study the atmospheres of exoplanets. And these are specifically planets outside of our solar system, so very complementary to what Stephanie studies. And my role on Webb is really just to ensure that we have all the tools we need so that we are ready to study the atmospheres of these exoplanets in exquisite detail with Webb.
Thanks, Nicole. Great. And I'm Laura Betts. I'm our public affairs officer for NASA's James Webb Space Telescope. So I'll be leading you through this discussion, and feel free to check us out at jost.nasa.gov or at NASA Webb on any of our social media handles for more content. So let's just talk about how exactly Webb will help us to see the cosmos. Amber, would you be able to speak to that?
Sure, yeah. So Webb is a telescope. And usually when you think about telescopes, you probably get a picture in your head of your typical, backyard telescope, which is a tube or a mirror at the end of a tube. So Webb is like that in that it's a giant mirror, but we're putting this giant mirror into space. And you'll, along the course of this discussion, see pictures come in of what the telescope looks like. And you'll notice it doesn't look like a typical telescope. It's not a mirror at the end of a tube. It's this giant, sci-fi looking thing. But what it is it's a giant mirror in space. Put together with some really cutting edge instruments that will allow us to learn incredible things about the universe. We'll learn about everything from the most distant galaxies in the universe, this sort of epoch near the beginning of the universe that we've never seen at all the way through looking at other galaxies, looking inside our own galaxy, looking at exoplanets, which Nicole mentioned, and then sort of our cosmic backyard of the solar system that Stephanie works on.
Amazing. Nicole or Stephanie, would you like to add to that?
Honestly, it's really just getting to see these heat signatures that we've never seen before. That's what Webb will allow us to see the cosmos, as we call it. So something that I think we're all really excited about.
Perfect. So Webb isn't just like any other telescope like Amber just described. It's an engineering marvel. So what makes it such an incredible engineering marvel? Kenny, would you like to answer that?
Honestly, there's a lot of things about Webb that really make it a cutting edge in itself. I think one of the most amazing things, something that actually blatantly jumps out in front of you, is the OTE, or the optical telescope element, which are the huge gold-plated mirrors that everyone sees, and everyone knows Webb for these gold-plated mirrors, right? So they're not only visually appealing as gold-plated mirrors, they're also their functionality is through the roof, and it really speaks to the technology that we've added, or the technology that we built on since Hubble's time, for example. So that, I would say, is one of the greatest engineering marvels outside of the fact that it's a giant tennis court size transformer that's flying around 1.5 million kilometers from Earth in the L2. So it's a lot of interesting components about it. But I think one that draws a lot of people to it is it's how visually appealing it is.
And what makes this telescope so challenging?
From an engineering point of view, so from an engineering point of view, just because it's so many moving parts, like I said earlier, it's a transformer in space, and it's wider than, I think it's wider than a tennis court. It's not as long, but it's wider than a tennis court. And it's just so many moving parts. And what makes it really different than Hubble is that Hubble is in an orbit that we could access. And so if we need to make a change, I say it simply, like we just go up and fix it. It's not that simple, but we can just go up and fix it. But no one's going to an L2 orbit to fix Webb, for example. So that's one of the main reasons why we're trying to make sure everything goes really smoothly here on Earth before we send it up. So challenge for those reasons, because it's far out, because it's cutting edge, because everyone will make sure it's right, and because of what it will discover for us.
So one of those elements you're describing is that sun shield. It's as large as a tennis court that has to unfurl in space. Can you tell me a little bit more about that? Like, why was it designed that way?
Yeah, the 5-layer kite-shaped sun shield. I didn't work on sun shield directly, but the sun shield was designed the way it is because how we need to keep the instruments at a very cold temperature. I think it's 50 degrees Kelvin, which is negative 370 Fahrenheit, or 233 Celsius, depending where you're watching this, something like that. So we had to keep one side of it is obviously going to be hot because it's oriented toward the sun, while the other side has to be cold so that it can get the necessary data that we need. But anyway, we made this really cool grid pattern for the sun shield that allows it to, if it's impacted by a meteorite, it controls where the damage is, so it won't really damage the sun shield too much. And that was the idea behind the grid pattern.
So that sun shield's protecting the telescope from heat light from the sun, the Earth, and the moon, right?
Mm-hmm.
Okay, so what's the point of the telescope? Like, what science are you all most anticipating exploring with Webb? Stephanie?
Well, so I'll bring it back to Earth, or close to Earth anyway. So in the solar system, I think some of the most exciting things that Webb's going to bring for us is actually being able to study things like ocean worlds, which is one of the hot topics right now in solar system science. So we have these moons, for example, around Jupiter and Saturn that have these big, thick ice crusts, but underneath we think there's a huge ocean underneath that crust. And we believe this because every once in a while they'll have these little poofs of gas that come out of them, which the Hubble telescope actually found for the first time on Europa, for example. And what Webb will be able to do is not only see the poofs in infrared light, so C is longer wavelengths, but we'll also be able to disentangle what that poof is actually made of, and then sort of connect the dots on what actually the oceans are made from beneath that icy surface. But even if we don't see them actively coming out of the ice, the gas coming out, we'll still be able to see whether the surface of that body is actually affected by any activity happening on these moons. So we'll be able to map kind of the composition of not only the plume or the gas or the poof, but also the surface around it, and see how that's altered, which will give us a lot of details that we really want to know before we go and explore some of these bodies for things like astrobiology and searching for life.
How is this telescope going to add to your science, Amber?
One of the primary science drivers in the very beginning, when we first started thinking about building this telescope, over 20 years ago, was to be able to look back in time and see the very first galaxies that were born after the Big Bang. And so look back in time, that sounds fanciful, but it's actually literally true. We can do that with telescopes. And of course, the reason for that is because light takes a finite time to travel through space. If you look at your light across the street, street lamp across the street, the light from that street lamp takes a teeny tiny fraction of time to cross the street and get to your eyes. The light from the sun, takes about 8 or 9 minutes to get from the sun to the earth. And so you're sort of seeing the sun as it was 9 minutes ago. And so you can sort of think about stepping further back in space. And so objects that are further away in space, we're literally seeing them as they were back in time. And so and that's one of the things that makes telescopes so awesome, is because the bigger telescope we have, the more distant and the fainter things we can see. And with the Hubble Space Telescope, we've made just absolutely remarkable strides in this. We've been able to look back in time and see some very, very early galaxies. But what we haven't been able to see yet are the very first galaxies that were born after the Big Bang. These baby galaxies that popped up just a few 100 million years after the Big Bang. Can't see that part of space at all. Never been able to. But with Webb, we're going to be able to pierce that veil that we've reached with Hubble and sort of see beyond and be able to see some of those first galaxies that were born in the very early universe. So for me, that's a really exciting prospect, because in this whole 13.8 billion year history of the universe, we've been able to see galaxies that are pretty far away. But we haven't been able to see how they got their start. And so Webb is going to allow us to sort of, fill in that first chapter of the universe and help us learn how galaxies got their start.
And Amber, when we talk about looking at stars, or looking, I know you mentioned looking at the sun, so definitely don't look into the sun, everyone. Doesn't matter 8 or 9 minutes, you see the difference. But something really cool about James Webb is the instruments on board, and how we won't see anything in terms of visible light, while instead it will be more of that infrared light, and making it different from Hubble in the sense that Hubble was focused on ultraviolet and the visible spectrum, and then James Webb will focus on more of that infrared stuff, which allows us to see through dust clouds, and I'll use the word plumes as well, dust clouds and things like that, so we can see even further. But yeah, we're super excited about Webb.
Perfect. And how about Nicole? What makes you excited about this telescope with your science?
The really nice thing about Webb providing us with these detailed infrared observations is that we can really, for the first time, start to look at in detail the structure and composition of the atmospheres of exoplanets. And this is something that it's really an exploding field, because most of the exoplanets known, they were discovered in the past 10 years or so. So we now know of over 4,000 exoplanets, and they have been studied at infrared wavelengths at all. Hubble's done some observations. There's also a Spitzer Space Telescope that was looking at some of these exoplanets, but we haven't been able to really dig into the really tiny absorption signals that come when you have a planet with an atmosphere blocking some starlight from our point of view. We want to look for those tiny signals that Webb will really be sensitive to. And this is especially the case for even smaller planets that are just being started to be studied, like planets around the size of Earth or a little bit larger. So we're trying to push to smaller and smaller signals, essentially. And Webb, that's really what we need Webb for. So I'm really excited to push, this field that's been growing rapidly. But we really need something like Webb, which is coming, now, to push even further.
Exoplanet scientists are glorified solar eclipse scientists.
So where's Webb at now, guys? And when is it going to launch?
Webb is somewhere a lot warmer than here, that's for sure. It's currently in Redondo Beach at Northrop Grumman, going through its final stages of testing and integration. We've actually completed all of our tests and integration, and we're now getting ready to fold the telescope up to ship it down to French Guiana for launch on an Ariane 5 later this year, around Halloween, actually.
Excellent. You can follow along on our website for anyone who's paying attention now at NASA Webb on any of our social handles to check out more features about where Webb is and what's happening with it. So I think a couple of you had mentioned that the Hubble telescope was so significant in our history of astronomy, but how does Webb compare to Hubble?
The biggest difference is the size. And size is everything for a telescope, because the bigger your mirror is, the more light you can gather. Like a telescope mirror is sort of like a light bucket, right? And so the bigger the mirror is, the more light you can collect. And where we're talking about looking at very faint signals, whether it be from exoplanets or from very distant galaxies, we need, a big mirror to catch all the light we can. And then also, the bigger your mirror is, the more fine detail you can see in the images. And so we need that huge mirror, and it is about 7 times bigger than Hubble's mirror. And the whole telescope, we've already talked a little bit about the size of the telescope, but it is huge. It is by far the biggest telescope that we've ever attempted to send to space. The mirror, as I mentioned, 6.5 meters across. The sun shield, we've already talked about, it's about the size of a tennis court. Top to bottom, it stands about 4 stories tall. So that's the first big difference. Hubble's about the size of a school bus, to give you a sense of comparison. And then Webb stands about 4 stories tall and is as big as a tennis court. So that's the main difference, or one of the main differences, is just the enormous size of this telescope. And we've also talked a little bit about the kind of light it will see. I think Kenny mentioned that this is an infrared telescope. So it will see the universe in light that's a little bit redder than what your eyes can see. Hubble's primarily a visible light universe. It sees the universe in light that your eyes can see. Also a little bit of ultraviolet and a little bit of infrared. But Webb is going to see the universe really in a whole new light. With this amount of sensitivity. And then of course, where it is in space, which I think Kenny has also mentioned already, Hubble orbits the Earth about 350 miles up. So it's pretty close to Earth, relatively speaking. That's why astronauts have been able to service it. Webb's going to be 1 million miles away. So it's another key difference between the two.
Stephanie, do you want to add any more to that?
I think my favorite comparison of Webb and Hubble is how the mass difference of the two facilities or observatories. So as Amber just said, Webb has a 6.5 meter diameter kind of composite mirror, and Hubble's just one single piece of glass. It's a monolithic piece of glass, and the mass of that mirror is actually almost twice of the mass of the James Webb Space Telescope's mirror. So it's just a tremendous amount of engineering that went into this to not only be able to build something so big that can unfold in space, but also being able to ship something like that up on a rocket that's that big means that you have to lightweight everything. And I think that's one of the coolest things, is just considering how much weight that we were able to save. And I'm hoping, I can get bone implants of this lightweighted material or something, it'll help with my gravity as well.
So Nicole, what makes you excited about this mission in terms of its technological capabilities?
One part of my excitement comes from really the first stages of the mission, where it's going to launch and literally unfold in space, like we said, like a transformer. I've never seen anything like that in my lifetime, and I'm really excited to see this feat of engineering come together. But beyond that, like in terms of science, there's always discoveries that we don't know are coming, essentially. So once we have this massive telescope in space with these really sensitive instruments, 4 different instruments looking at all these different infrared wavelengths of light, I mean, we are most likely going to make some unexpected discoveries. And that just continue to add to our knowledge. So I'm really excited about what is planned, but also what we don't know is coming in terms of science.
Very cool. So for each of you, what is the most amazing fact someone should know about this telescope? We can start with Kenny.
Let's see. The most amazing fact that I would say we should know about the telescope. I feel like we talked about it a lot from kind of my nerdy science mind. I like the concept of red shifting, which I won't really get into here, but I really like that concept. And I won't get into it because I don't fully understand it. I just know it enough to explain to myself. But just how Webb utilizes that phenomenon to thus, peer back in time. And again, we're going into the infrared light, blase, seeing through the dust clouds and things like that. So that's the first thing. The second thing is just the amount of time that has been spent developing this telescope. I think everyone knows that the project has been going on for years, but just the amount of teamwork and effort that went into something like this, and how make its footprint for years and years and decades to come. I think it's something that everyone should really appreciate.
So Kenny, adding on to that, so you say that there's this massive team working on this project. It's not just NASA. Who else is working on this project?
So it's not just NASA. There's NASA. There's Northrop Grumman. There's the European Space Agency, the Canadian Space Agency, and it's really a global effort here. And it's different team players coming into play, and it really shows that, again, we as a collective, as humans, are trying to understand the universe we all live in better, regardless of where we're from, regardless of what language we speak, XYZ. We're all in this together to make these discoveries.
Thanks. And what's it like working with teams from all over the world on something like this, especially for Stephanie or any of the scientists here on the panel? How does that work exactly? I feel like that's hard for people to wrap their heads around.
As a scientist, we're used to working with people all over the world on our projects. I personally have collaborators, all the way from East Asia into Europe and even in South America. So it's something we're pretty used to working on as far as science goes. Working on a project, though, is a whole different level, because now you're trying to, get your engineering meetings organized with people in Europe and, on the West Coast. Right now, the telescope's in California. So, we have meetings that last, well into the late evening. And people in California are waking up at 5 a.m. for, their first meeting on, the East Coast or in Europe. So there's definitely challenges, especially in a telework environment that we're in right now. But I would say, as far as the science team goes, it's been tremendous, because as Nicole was saying, there's so many unexpected discoveries. So bringing people in that have been thinking about this telescope from all over the world really broadens the horizon and the scope of capability for this amazing observatory. Just the unprecedented sensitivity, the wavelength coverage, the capability of this telescope has really opened the imagination of scientists basically all over the world. And that's been the most fun for me, is working with all these people, making sure this telescope can do the things that they want to do with it.
Definitely. And why do you all think that this drive to explore is important in general? Why should we care to build an awesome telescope like this one? Amber?
Well, I think that this drive to explore and learn and discover, it's sort of, it's innate, right? It's in all of us at some level. Some of us more than others, I guess. But you can't help but go outside, in a dark site and look up at the sky and wonder how it all works, how it all got here. That's how I got my start as an astronomer. I grew up in rural Arkansas, where there was nothing. So the sky was really dark. And it just, a dark sky always sort of instills that sense of wonder and questioning. And I think it's just part of who we are as humans. to try to learn more about the world around us. And I think it is, I mean, I'm biased, but I think it's one of the most pure and beautiful endeavors that humans can do.
It's true. What about you, Nicole? Like, why do you have this drive to explore so much?
A lot of what Amber said, about just wanting to understand really how things work, first of all. But for me too, I've always been interested in other planets, exoplanets, ever since I can remember, honestly. And part of that came from wanting to understand what is our place in the universe, like, literally. Like, as humans, what are we doing here? Are we the only ones around, right? And is there any other planet out there that could potentially sustain life, either life that we've never seen before or life as we know it here on Earth, So that's what drives me to explore, although that keeps me within our galaxy very much, because all the planets we know of right now are only within our own galaxy. So, we're not getting back to the beginnings like Amber can get to, but, we have to start somewhere. And so that's I think what is part of it. Everybody's always wants to know, oh, what's the answer to, like, why are we here? And that's part of what drives me, at least, and I think it does drive a lot of other people as well.
So question for Kenny: how do you feel working on this project?
I felt like it was honestly a once in a lifetime experience. Working on something just this absolutely massive. In itself, when you look at its individual subsystems, when you look at, OTE, which I mentioned earlier, and then you have ISOM, which is where the instruments sit, then you have the sun shield and the spacecraft bus. When you see each of these huge components clearly being integrated together, kind of right in front of you, with multiple tests, I thought I was really, really fortunate to have the opportunity to do that. We'd bunny up and we'd spend probably 5-6 hours in the bunny suit, take lunch, and then you could do some more.
Very cool. So you're able to actually touch the telescope that's going to go 1,000,000 miles out into space and put those parts together.
With all the right precautions. I was grounded, had my cuff on. I was fully bunnied up.
Awesome. Very cool. Now, Stephanie, how do you feel about working on a mission like this? Something that's so historic.
Well, I hope it's not a once in a lifetime opportunity. We're already working on what the next big mission is going to be for NASA, and so hopefully we have even bigger and better things in the future. So, but I will say this has been a tremendous experience for me. Coming from the planetary science community, we're usually building missions that are going to go to Mars, or they're going to go, orbit Saturn and, study it for a decade, or, we want to fly by Pluto. So this is just a whole different realm of being able to study not only those individual objects, but everything in the solar system. And then the discovery space across everything in the solar system, which is absolutely amazing. So I think there's a lot more to come. And again, I hope it's not a once in a lifetime opportunity.
How about you, Amber? How do you feel working on a project like this?
I guess the word that comes to mind is grateful. It just, to be involved in a mission like this, that I do truly think that this telescope will surprise us. Nicole touched on this a little bit, but every time we send a huge, big, bold, ambitious telescope into space, we learn things that completely surprise us and that make us really step back and rethink how we even think about the universe. That happened with Hubble. I think it'll happen with Webb. And so just to be able to be a part, a little part of this big mission is really, it's been a lot of fun. And I'm really grateful to be a part of it.
Thanks. And Nicole, how do you feel?
It's about being grateful, certainly, but it's also just a great learning experience, because we are preparing for these missions, to come next after Webb. But we also have a lot of active missions at NASA that, I think a lot of us here work on multiple missions already. So, it's a very different experience working on this gigantic like flagship, transformer going into space compared to some other missions that we work on. So
we're getting really excited for this amazing mission that's bigger than any rocket that can send it into space. So it has to fold up like origami and open out in space like a transformer. What keeps you all up at night thinking about that process? So let's go with Kenny first.
So that process in itself, just the amount of time it takes to A, get to its orbit, then B, deploy in its orbit is taxing on the mind, I'll say. And I don't want anyone to think that, okay, it's launch day, it's been 24 hours, where's the data? Like, it's not going to be that quick. It's actually months before we'll get a chance to actually see. It's months before scientists will get a chance to see the data, and then probably months after that before the public is able to see any data. So I think it's just the process of getting to the orbit and then fully deploying for me. Those are the two things I constantly think about.
How about Stephanie?
Well, yeah, the deployment. But I think one of the most comparable things that I have as far as just the whole mission getting where it needs to go is, so when the Mars Science Lab landed on Mars, they had this whole 7 minutes of terror of, the spacecraft had to release the rover and it had to parachute down through the very thin Martian atmosphere and land safely. And well, we have a little bit more than 7 minutes of terror. It's closer to a month. I don't know if it's terror, but it's definitely terrifying for those of us that have been working on the project. I'm very confident in what our engineers have been able to do, though, here on the ground. So I don't think I have much fear of everything working. I think my biggest fear is, how much more proposals I need to write and how much time it's going to take to get ready for the next thing. But yeah, I think that's probably my 2 cents on it.
How about Amber? What keeps you up at night with this telescope?
Yeah, that's essential deployment. But like Stephanie, I trust Kenny and I trust the engineers that have really, poured their lives and their souls into building this telescope and spent literally years testing it. I think that's the really important part is that, as Kenny mentioned, once it's in space, we can't go fix it like we have Hubble. It's a one-shot thing and we got to get it right. And I know that the engineers have spent years, testing to make sure that we do get it right.
Would you like to add to that, Nicole?
If anything, I would say, what keeps me up at night is just how close the launch date is actually getting. Like it's really coming. It's like, oh, this is becoming even more real every day. And have we done enough to prepare? Like, are we ready for this beautiful data that's going to come from this telescope? What else can we do now, to prepare for it? So I think I'm pretty comfortable trusting the engineers, that the deployment's looking fine, everything's good. Yeah, 2 thumbs up.
Great. And now, Kenny, can you tell me a little bit more about the testing? So as I understand it, the telescope has been tested all around the country at different NASA centers. Parts have come from other parts of the world. And there's all these different stages and checks to that testing to make sure that everything is going to work properly in space. Can you talk about a couple of the major tests that this telescope has endured?
Because we're being conscious of time here, I'll say the quickest things I can say is that even on a component level, all these different parts of each subsystem are tested. So thermal tests, cryo tests, yada, yada, they're all tested. One of the most popular tests I'll say that a lot of people can physically not see, but a lot of people would immediately understand it is the vibration test. So, you can go through the different subsystems where you put it on this huge shaker table and you just shake it. And it just simulates a rocket launch because when you fold it up like origami and it's in that configuration and the rocket's taking off, we want to make sure bolts stay in place. We want to make sure screws stay in place. We want to make sure the instruments are safe, everything stays connected. Because again, one-shot thing. So there was a number of tests, but I would say one of the immediate relations are vibration to a rocket launch. Bam.
Excellent. Anyone else want to add any more about the interesting tests that the telescope had to endure?
I think the end-to-end optical test that we did down in Johnson was probably one of the most important ones to make sure we got it right. So this was sort of the test to correct all of our faults that we made with Hubble when we launched, not making sure that the optics were working the way that they were supposed to be working, and so we were very careful to make sure that that was done on the ground for Webb, so that we don't have to go and put glasses on it, because again, we're not going to go all the way to L2, a million miles away, to start trying to fix this telescope. So I think that was probably the most important one from my perspective, as a scientist that wants data in the telescope.
And you're also saying that this telescope's different because you're actually focusing it in space, right?
Yeah, and we actually have real-time focusing mechanisms on the mirrors. So the mirrors all move independently. There's, these little hexagons that are all strategically placed to make it look like one mirror. But they all move independently, and we're actually going to test that real-time in space and actually try and focus the mirror as we're there and make real-time corrections, as opposed to having a fixed position and just kind of being stuck in a situation that wouldn't necessarily be optimized. And that's something we're going to do throughout the entire mission. So it's not something that's just a one and done. As the telescope gets older, if a micrometeorite happens to hit one of the mirrors and knock it out of place, any of those kinds of things actually will be fixed in real time. And so that's really a nice thing.
That's super cool. So before we wrap up, I just want to thank everyone for all of your expertise and all of your points, and for sharing the story that with the world of you working on such a tremendous telescope. But before we wrap up, what's one thing that you hope anyone watching will understand about this mission? So let's go with Stephanie.
We're going to rewrite the physics and astronomy books with this telescope. The new discoveries to be made, even the anticipated things that we're already planning for and excited to do, are already unprecedented. We have orders of magnitude and sensitivity. We're going to see things that we haven't had access to before, not only in the solar system, but throughout the entire universe. And I think all the discoveries to be made are something to be sitting on your hands and waiting anxiously for.
Thanks. How about you, Kenny?
So I'm excited, or what I hope everyone understands is that when the satellite goes up, we say we hope we find this, we hope to find that. There's really a gray area in terms of, like Amber mentioned, every time we send something new into space, we might discover something that we didn't expect to discover, for example. So I think the gray area for me is really the most exciting part of, that we didn't plan for that, but it's really interesting. And then using other data we have, we might be able to then take off and use it in other ways. So the gray area is what that's.
Excellent. And Nicole, for you?
Beyond the science, just how much of a feat of engineering this has been, and how many amazing engineers and scientists have worked on this to make this happen, to go from just a vision to a reality very soon. And I think, I want to say there's something like over 1,000 people have worked on this, maybe even more. I'm probably underestimating. So, there's a lot of people who put a lot of work on this over the years. And
all right, Amber, what about you?
I think I would just say that, people think of things like telescopes and they think, oh, that's a toy for astronomers. But, these types of machines are for everyone. They're for the whole world. And in fact, when the data comes back, anyone in the world can go and access the data. It'll all be available online. And I think just that concept that these aren't just astronomers' toys, that this is a facility for the world that will change our understanding of how we fit into the universe.
Thanks. Okay, thanks so much, everyone, for all of your expertise and for sharing all of your work on this amazing telescope, NASA's James Webb Space Telescope, launching this year. And thanks to everyone watching for the privilege of your time. Take care, everyone.